Hello and welcome back to another Math 104 lecture. So in our last lecture, what we were looking at was we were examining different kinds of equations, right? So where we talked about linear equations, where that was x to the first power. We talked about quadratics, where that was x to the second power, like, and those were our highest powers. And now we were examining a wide array of other equations, such as powers higher than 2. We did a couple examples of those. We talked about rational expressions, so polynomial over polynomial inside of an equation, and we talked about a little bit about square roots. So picking up from that lecture, what we're going to look at today is we're going to look at a little bit more with radicals inside of equations. Then we're going to talk about rational exponents. So if you remember, that's a rational exponent is basically just a fraction exponent. So we're going to see that. And last but not least, what we'll look at today is we'll look at substituting an equation that doesn't necessarily look like it's in quadratic form, but substituting in so that way it can be a quadratic. And then we just apply our normal quadratic, principles to it, our normal methods, but just with a slight twist at the end. Okay, so before we get to that, I just want to touch on one quick thing that I did not touch on in the last lecture. So I'm bringing this example back up. So in the last lecture, we looked at x to the fourth is equal to 4x squared. And when we solved it, when we did all of our work, we found out that there were 3 solutions, right? There was 0, -2, and +2. As written, I have it 0 and then plus or minus 2. And also what we found out was 0 had a multiplicity of 2, right? So the one thing that I didn't touch on, which I really think is very important for your understanding, is when you're solving this, one thing that you might be tempted to do is you might be tempted to divide by your variable in an effort to make things, a little more simple, right? So what do I mean by that? Well, let's say, again, we're trying to solve x to the fourth is equal to 4x squared. And let's say you, fell into your temptation and you divided both sides by x squared. And now for the purpose of this, I'm going to write the rest of this in red ink because I really want to illustrate that this is incorrect. You cannot do this, okay? And we'll see why you cannot do this in just a second. So we're going to divide by x squared and x squared, right? So what is that going to leave us with? Well, x to the fourth divided by x squared leaves us with x squared, right? You just subtract the exponents, okay? And then over here, subtracting the exponents, it would be x to the 0, which is just 1, right? So 4 times 1, and we would get 4 here. And we all know that you have 2 different ways to solve this. You could either take the square root of both sides, or you can move the 4 over, and that's what I'm going to do. I'll just make it x squared minus 4 is equal to 0. This is now a difference of squares. We can plainly see that. So we would get x plus 2 times x minus 2 is equal to 0. And when we solve this, we would get x is equal to our 2 solutions of plus or minus 2, right? Our 2 solutions, one is -2, one is +2. Okay. What is the key difference between here and our original solution? Well, the key difference is that we're missing that 0, right? So what we're essentially saying is we're missing a solution. And actually, because we divided by x squared, and because we realized that 0 had a multiplicity of 2, remember multiplicity means the factor was counted twice, we're actually not just getting rid of one solution, we're getting rid of 2 solutions. And so when we're solving x squared minus 4, is equal to 0, notice that we only got 2 solutions, and that matches, the highest exponent that we have in our equation, which is a square, right? X squared. So the reason that we can't divide by our variable when we're trying to solve for our variable is because when we divide out by our variable, we are essentially getting rid of solutions. And we can't have that. We're trying to find all of the possible solutions that would satisfy the equation, and 0 is a solution that would satisfy the equation, right? If you plug 0 in, 0 to the fourth is 0, and then 4 times 0 squared is just anything times 0 is still 0, so we get 0 is equal to 0. So obviously 0 is a solution, and by dividing by x squared, we are omitting that solution. So I just wanted to touch on that quickly because I feel like that's important to go over. I don't know if anybody has really told any of you that before, but that is why we can't divide by our variable. Okay, so with that being said, let's move on to new material here. So when we left off last time, again, we were dealing with square roots, right? So what I want to do now is I want to talk about what happens if in your equation you have not 1, but 2 roots. So let's look at an example. Let's say I have the square root of x minus 5 plus the square root of x, and this is equal to 5. Okay, so you look at this and you say, well, if we recall, what we were doing last time is our plan was we wanted to isolate the square root, right? And we wanted to square both sides so that way it would cancel with the radical, right? And we would just be left with whatever's in the radical. But remember, if we try squaring both sides as it is, if we square both sides, we have to square the entire quantity, right? And things aren't going to cancel as neatly because we're left with an a plus b squared situation, right? And we know that when you have a quantity of a plus b being squared, you're always going to get that middle term of 2 times a times b, right? So things aren't going to come out necessarily super cleanly. So I don't want to do that. What I want to do instead is, so we have x minus 5. It was a plus square root of x is equal to 5. So what I want to do instead is I want to just isolate one particular square root. And it actually, you'll find it doesn't matter which one you isolate. For the purpose of this, I'm going to isolate the square root of x minus 5. I'm going to keep that one by itself. So we keep it by itself, so square root of x minus 5. And what does it mean to isolate? Well, it means you're getting rid of everything that's on the same side as it, right? So I'm going to move over my square root of x. So we have 5 minus the square root of x, right? We're subtracting square root of x from both sides. It's going to cancel on the left. We have the negative version of it on the right. Okay, so now what we're going to do is we are going to square both sides because now we're not going to have both squares on the same side, giving us that really crummy middle piece. So we're going to square both sides, and that means we square this, and we square this entire quantity, including whatever operation was happening in between, right? So now we have, okay, well, this part should be easy on the left. Our square is going to cancel with our square root, just like before in our, original examples. So we're left with x minus 5 here, right? And now what we see here is we're still ending up with, one of our quote unquote popular cases, right? We're ending up with an a minus b squared. And for those of you who, again, don't remember, you can just FOIL this out, right? This would just be equivalent to 5 minus square root of x times 5 minus square root of x. You could FOIL it. You'll arrive at the same answer that I'm going to get. But I'm going to use our blueprint because I remember that a minus b squared is equal to a squared minus 2ab. Remember, the negative is as a result of the same negative inside the parentheses, plus b squared. Okay, so what does this mean for our blueprint? Well, it essentially just means, well, a squared is 5 squared, right? So 5 squared is 25. We have a minus 2ab. So minus 2 times 5, which is 10. So minus 10, and b is square root of x, right? So minus 10 square root of x. And last but not least, we have a plus b squared, which is plus square root of x squared. And all that's going to happen there is that the square is going to cancel with the square root. So we just get a plus x, right? So I just did that according to our blueprint, but feel free to FOIL it out. You'll arrive at the exact same answer that we have on the right side when it's expanded. So now what we're going to do is we're just going to do some simplification. So simplifying, well, we have an x on one side, an x on the right side. I'm going to subtract the x from both sides. And this is different than dividing x from both sides. I just want to clear this up. If you're subtracting it, it's much different than actually just getting rid of one of your solutions. So we subtract x from both sides, and we're left with negative 5 is equal to 25 minus 10 square root of x, right? We subtracted x from both sides. It's going to cancel here and here. Okay, so now what we're going to do is we're going to kind of just shift things over. I have a negative 10 square root of x. I just want to make it positive, so I'm going to add it to both sides. So we get 10 square root of x over here, and it canceled on the right. And I'm going to add 5 in the same step, so because I want to put my 5 over with my 25. And so we add 5 to both sides, and we get 30, right? And now this is looking a lot easier, and the reason it's looking a lot easier is because now we only have one square root. Notice that when we squared both sides, we got rid of one of the square roots because it was isolated, but we still had to deal with one more, right? So when you have 2 square roots in your equation, or 2 roots in general, you're going to have to do the process twice. If you have 3 roots in your equation, you're going to have to do the process 3 times, so on and so forth, right? So we are left with one square root remaining here. So that means we're going to do the exact same thing. We're going to isolate our square root, and then we're just going to square both sides to get rid of it. So isolating means I have a multiple of 10, so I'm going to divide both sides out by 10. So dividing both sides out by 10, we are left with square root of x on the left, and 30 divided by 10 is 3. And our last step here is we want to get rid of that square root, so we're going to square both sides. So squaring both sides means it's going to cancel here and here. We're left with x is equal to 3 squared, which is 9. And we're almost done, right? But remember, extraneous solutions, right? Extraneous solutions can occur in one of three situations. They can occur in rational expressions when your variable is on the denominator. They can occur in radicals, which is what we have here when you have an even indexed radical, right? We have a square root, the index is 2, it's even. So that means we can technically get an extraneous solution. And the third case is something that we haven't come across yet, but we will later, which again is logarithms. So we see here, oh, wait, we have square roots. Our variable is under a square root. We might actually have an extraneous solution. We need to check. So checking, we're going to write our check over here. Wherever there was an x, we're just going to put in our 9, right, to check. So we're going to have the square root of 9 minus 5 plus the square root of 9 is equal to 5, right? It's equal to 5. Okay, so 9 minus 5 underneath the radical, that gives us square root of 4. And remember, because we're not solving for a variable, we're only doing a check, right? The square root of 4, we only need to consider the positive value. So square root of 4 is just going to give us 2 here. And square root of 9, once again, only consider the positive value. So square root of 9 is just going to be plus 3. And hooray, 2 plus 3 is 5. We know that it checks out. So this is not an extraneous solution. Our solution set, you can just write the curly braces around the one number. Our solution set is just 9. X is equal to 9. So that's it. So again, just to recap what we did, we saw that we had 2 square roots. What we did is we isolated one from the other. We squared both sides, and when we do that, we realized, oh, well, we still have this crummy middle piece here that involved our square root. So we had to repeat the process by isolating our square root all over again. And then, the same process fell out. We ended up with x is equal to 9. So I am going to give you guys an opportunity to try this with the first classwork assignment. So the first classwork assignment is as follows. You have the square root of 2x minus 1. This is minus the square root of x minus 1. And this is equal to 1. So feel free, go ahead and give this a shot. See if you can figure it out, just doing the exact same processes that we've been doing over and over. Okay, so hopefully you guys paused the video. It wasn't too bad. Let's go ahead and solve it together. All right, so first step, right? We have 2 radicals. We want to isolate one of them. So I see I have a negative square root of x minus 1. I'm just going to move that over, make it positive on the right-hand side, right? So we are left with square root of 2x minus 1 here. And adding square root of x minus 1 to both sides cancels on the left. We get 1 plus square root of x minus 1. Okay, so now we have to get rid of the first square root, and we do that by squaring. So we square the left, we square the right, and that's going to cancel, that's going to cancel. We're just left with 2x minus 1 on the left-hand side, which is exactly what we want, right? We're trying to cancel the square roots one at a time. So now over here, we have 1 plus the square root of x minus 1 squared. Well, once again, we have a plus b squared, right? And a plus b is a squared plus 2ab plus b squared. Feel free to FOIL this out if, again, you're not remembering these blueprints, but it really helps you, I promise. It really helps to remember this so that way you can just plug and chug, right? So let's plug in. We know a is 1, so that means we're going to have a 1 squared, right? Which 1 squared is still just 1. We have that middle piece of plus 2 times a times b. So plus 2 times 1 is still just 2. So plus 2 times, and b is going to be that whole piece underneath that radical, including the radical. So plus 2 times x minus 1. And then plus b squared. And b squared is the radical of x minus 1, right? So what's happening? Well, it's just going to cancel out the square root and the square. So we're just left with plus x minus 1. Great, let's go ahead and start simplifying and doing some things, right? So we see that we have an x on the right, we have a 2x on the left. I'm just going to subtract an x from both sides. So we're left with an x here minus 1 is equal to, and we can do a little bit more simplification as well, right? We have a 1 and then we have a minus 1 at the end, right? So these are going to cancel as well. So all we're left with is the 2 times square root of x minus 1 on the right-hand side. Okay, well, all we have to do is we have to go ahead and we have to square both sides, right? Because we're trying to get rid of the square root. And by doing so, before we do that, we have to isolate it, right? So to isolate it, we're going to move that factor of 2 over. It's being multiplied by 2, that coefficient. So to undo multiplication, we divide. We get x minus 1 over 2 is equal to square root of x minus 1. Okay. And let's go ahead and square both sides. So squaring both sides, we get x minus 1 here. We get x minus 1 over 2 squared, right? Okay, so x minus 1. And what's happening up here? So remember, your exponent in a fraction applies to both the numerator and the denominator, right? So the denominator part's going to be relatively easy. We have a 4. And we have up top x minus 1 squared, right? I'll even write this one out. So x minus 1 squared. And what do we see once again? We have a minus b quantity squared. And I'm not even going to write out the blueprint because we just did it before and we just did the a plus b, which is very similar. So the blueprint, I'll speak it, is a squared minus 2ab plus b squared, right? So writing this out, we have up top x squared minus 2 times 1 times x, so minus 2x, and then the b squared, which is plus 1 squared, which is 1. And this is all over 4 is equal to x minus 1. Okay, we don't like fractions, right? We want to get rid of fractions, so multiply 4 on both sides. We get x squared minus 2x plus 1 is equal to, and remember, when you multiply the 4 to both sides, you're distributing that 4 to each piece, right? So 4x minus 4. Let's go ahead and condense terms. We want a 0 on one of the sides, right? Because we have a quadratic now. So we're just going to set one of the sides as equal to 0. So minus 4x from both sides, we get x squared minus 6x, right? We have a negative 2x. Subtracting 4x from it is a negative 6x. And we have a plus 1. We have a negative 4, so we want to add 4 to both sides. So positive 1 plus 4 gives us a positive 5. This is still equal to 0. Okay, almost done, right? We have a quadratic. It's in standard form. Let's try to factor it. Let's see what happens. So factoring, we only have to look at c, which is our constant, right? Plus 5, because the coefficient to x squared is 1. So we don't have to do that a times c step. So looking at factors of 5, that will multiply to give us a positive 5 and add to give us a negative 6. We know that that's just going to be negative 5 and negative 1, right? Negative 5 times negative 1 is positive 5. Negative 5 minus negative 5 plus negative 1 is negative 6. So great, that works out. And zero product property says we can go ahead and split these up. And we know that when we split it up, x minus 5 is equal to 0. X minus 1 is equal to 0. We get x is equal to 5. X is equal to 1. And our solution set is 1, 5, right? Okay, so let's real quick go back and we realize, are we done? No, we're not done, right? Because our variables were underneath an even powered root. We have to do a check to make sure that our solutions are actually our solutions, right? So we go over here and we do a check for each of our solutions. I'm going to check the x is equal to 1. Okay, so let's do that one first. So we plug in 1 for wherever we have an x. We get square root of, we might not have enough room. Give me 1 second, guys. Sorry. So, oh, it's not scrolling. There we go. So we have the square root of 2 times 1 minus 1, right? So wherever we had an x, and then minus 1 underneath the square root. So minus the square root of 1 minus 1. And this should be equal to 1 if everything comes out correct. So let's see if it does. So 2 times 1 is 2, minus 1 is 1. So we have the square root of 1. minus 1 minus 1 is 0, square root of 0. Okay, remember, when we take the square root of a number, when we're doing our checks here, we're not solving for a variable. We only care about the positive value. So square root of 1 is just 1. Minus square root of 0, well, square root of 0 is just 0. So 1 is equal to 1. Hooray! 1 is, in fact, a solution. Okay, we go ahead and now we're going to check x is equal to 5. All right, same thing. So square root of 2 times 5 now, minus 1, minus, 5 minus 1 is equal to 1. Okay, so 2 times 5 is 10, minus 1 is 9, right? So we get the square root of 9 minus, okay, 5 minus 1 is the square root of 4 is equal to 1. Okay, so square root of 9 is going to be 3. The minus sign drops down. Square root of 4 is going to be 2. And 3 minus 2 is also 1. So both of these are solutions. Neither of them are extraneous. Hence, our solution set stands. Our solution set is just 1, 5. So yay, it worked out. Okay, so I know that it can seem a little daunting, but the entire idea is really nothing new, right? All we're doing is we're isolating our square root, we're squaring both sides, and because we had 2 square roots, we just had to do it twice. When we did it twice, we ended up with our quadratic. And then because we have a quadratic, we just apply normal quadratic rules to it, right? You didn't have to factor this. You could have done the quadratic formula. This quadratic formula would have also spit you out 1 and 5. So either way, totally works. The same things that work for a quadratic would work in this case because we got a quadratic. And then all you really had to do was realize, oh yeah, we had an even powered root. We need to check for extraneous solutions. You must check for extraneous solutions. So great, 1, 5, we're done, right? Okay, so let's move on to rational exponents being in our equations. So again, the best way to tackle this is just to start with an example. So let's say we had 2 times 2x minus 1, and this is going to be to the 3/2 power. Minus 30 is equal to 24. Okay, so what does the 3/2 power? Again, let's just do a quick recollection, right? What does this mean? Well, if we have any number, I'm just going to say a, right? I don't know why I drew this line. Wasn't thinking ahead. If I have a to the 3/2 power, right? The numerator of the exponent tells us the power of our base, right? So our base is always going to be the same. It's still going to be a, and the numerator tells us what the exponent is of a, right? So our numerator is 3, so it's a to the 3rd. The denominator tells us the index of the root, right? So it also means that we're taking the square root. Why? Because again, it is the index of 2 because our denominator is 2. And we also talked about that you could do these operations in either order. So you could do, technically, the square root of a first, and then you could cube it. And it doesn't matter which order you do it. All that matters is that you understand that you can flip back and forth between radicals and rational exponents. Okay, so this is just, again, a brief reminder to you guys what the numerator and denominators mean when you have that rational exponent. So, okay, so essentially, instead of it just being one term or one number with, it being a, we have everything inside of the parentheses now to that 3/2 power. So what we're going to do is we're going to try to isolate that term to the 3/2 power. We're going to essentially do very similar things that we did when we were just dealing with a square root. So what I'm going to do is I'm going to add 30 to both sides in an effort to start isolating. So adding 30 to both sides, we're left with 2 times 2x minus 1 to the 3/2 power. And when we add 30, 24 plus 30 is going to be 54, right? Okay, let's go ahead and divide both sides out by 2 because we have that coefficient of 2 in front and we're still trying to isolate. So dividing both sides by 2, we're left with 2x minus 1 to the 3/2 power. Great, we've now isolated it. And 54 divided by 2 is 27. Okay, cool. So what do we really have to do here? Well, you can think about it in one of 2 ways. You can either think about it as I need to reverse whatever operations are happening to the 2x minus 1. And the operations that are happening are I'm taking the square root of it and I'm also raising it to the 3rd power, right? So I need to reverse each of those operations, Or what you could do is you could convert it to radicals and do the exact same thing, but just with radicals. So I'm going to show you both ways, and I'm just going to do that. So if you're talking about converting it to radicals, well, we just did a quick reminder of the conversion, right? So converting it to radicals, this is going to look like 2x minus 1. And what I want to do is remember, because they're essentially equivalent and it doesn't matter which operation you want to put on the outside, I'm going to put my cube on the outside. And we'll see why in just a second. So the square root of 2x minus 1 all being cubed, right? And you agree with me, that's what's happening here, right? I have the 2x minus 1 in parentheses. It's the numerator of my fraction exponent is a 3, so that means I'm raising that whole piece inside to the third power, but the denominator tells us we're taking the square root of it, right? Okay, so we have this to the 27 is equal to 27. So what I want to do now is I want to just take the cube root of both sides. So taking the cube root of both sides is going to undo the raising of the to the third power. So we do this, and whatever we do to one side, we do to the other side, right? So we are now taking the cube root of the left and the right hand sides. And what should end up happening is, well, that's on purpose because that's going to cancel with this here, right? So now all we're left with is the square root of 2x minus 1. And when we take the cube root of 27, of positive 27, it's just 3, right? We're looking for a number that when multiplied against itself 3 times is going to give us 27. Well, 3 times 3 is 9, times 3 is 27. So the cube root of 27 is just 3. And, well, this should be really simple now because we know how to deal with, just a square root. Well, you just square both sides, right? So squaring both sides, you're going to get 2x minus 1, and I'll even write it, squaring both sides. And we know that this is going to cancel with our square root. So we just have 2x minus 1, and then 3 squared is going to be 9. Cool. And we can solve this, adding 1 to both sides and then dividing by 2. So we have 2x. We added 1 to both sides, and then dividing by 2, x is equal to 5. Hooray! We solved it, right? Okay, and then the other way that I just wanted to illustrate is, okay, again, so we're starting with 2x minus 1 to the 3 halves power, right? When you look at this and you say, well, what did we really end up doing? We were just reversing the operations of that fractional exponent, right? So if I had my 2x minus 1 to the 3 halves power is equal to 27, to undo that, we would raise it to the 2/3 power, right? So I would raise this whole thing to the 2/3 power. Why am I doing that? Well, remember, if we have any number, right, and it's raised to an exponent already, so we have 2x minus 1 raised to the 3 halves power, and then we raise it to another power, so in this case, we'll say m, all that ends up happening is that we multiply them together, right? We multiply the exponents, so n times m. Well, what do we expect is going to happen when we multiply 3 halves times 2/3? Well, multiply it out, right? We multiply fractions by multiplying across. So 3 times 2 in the top is going to give us 6. 2 times 3 in the bottom is also going to give us 6. So 6 over 6 is just going to give us 1, which means we should just end up with 2x minus 1, right? 2x minus 1 to the first power is just 2x minus 1. Any number to the first power is just that number. So what we're doing is we raise the left-hand side to the 2/3 power. So I'm also going to raise the right-hand side to the 2/3 power. So essentially, we're just skipping the step of converting it to radicals and then doing the operations that make sense for, each piece. All we're doing is we're saying, oh, we have a fraction. To undo a fraction, right, to make it equal to 1, I'm just going to multiply it by its reciprocal. So the reciprocal of 3 halves is 2/3. So great. Okay, so we're raising both sides to the 2/3 power. Again, we know that we're going to get 2x minus 1 to the 3 halves times 2/3. And again, we'll just bring down the 27 to the 2/3 power. Okay, we again expect 2x minus 1 to be our base, and then we get a 6 over 6 situation. 27 still to the 2/3 power. Not doing any simplification yet. I'm just showing you guys the operations that are happening on the left-hand side. And again, 2x minus 1 to the 6 over 6 is just 2x minus 1. So 2x minus 1, right? These are going to cancel out. We're just going to, oops, that was supposed to be red. Sorry about that. Those are going to cancel out and just leave us with a 1. So 2x minus 1 to the first power is just 2x minus 1. Okay, great. And now we can go ahead and simplify our 27 to the 2/3. What does this mean once again? Well, it means that we are raising it to the power of 2, right, where it's being squared. However, we're also taking the cube root of it, right, because that's what the denominator of the fraction means. And I think it's easier to go down first to take the cube root than it is to square 27 and then take the cube root of whatever that very large number is. And that's why I told you guys, because it's equivalent, you guys might find it easier to do one operation versus the other in terms of order. So I'm going to take the cube root first, and taking the cube root of 27 is just going to leave me with a 3. And then remember, we still had that square going on, right? So 3 squared, and we get 3 squared is equal to 9. 2x minus 1 on that left-hand side. And oh, wait, this is exactly what we had before. So we know that x is going to be 5. And that's it. So there were 2 different methods that you could think about, but you're really doing the same thing. I believe that the right-hand side, so I'm talking about this side over here, I think that this is a little bit easier because all you're essentially doing is you're taking whatever your rational fraction is, your rational exponent, and you're just raising it to the reciprocal power. So you're just raising it to the flipped fraction. And then whatever you do to the left side, you're also doing to the right-hand side, right? The left side might make a little more sense to you at first, but you're also doing a little bit more work, right? You're converting it to the radicals, then you're undoing the radical, then you're raising it, and you know, it's the same exact thing. You're doing the same procedure. It just takes a couple more steps. Okay, so however you want to think about it is totally fine. You'll end up with the same answer either way. And we get, again, x is equal to 5. And we're almost done, but remember, in our original equation, we have our variable, you know, right over here, 2x, and x is, you know, in there, right? And it's being raised to the 3/2 power. Remember that that means we're essentially taking the square root of our variable at some point. Our variable is underneath of a root. So we have to go ahead and check for extraneous solutions because our root was even. It was a square root, right? That's what the denominator of our rational exponent means. So we have to plug 5 back into our original equation to see if it's actually going to work out or if it's an extraneous solution. So let's go ahead and I'm going to erase this on the right side here so that way we can write our check over here. Okay, so writing our check, we have check right here, and we only have one solution that we need to check, so lucky us. So our original equation is 2 times 2 times 5, right? X was equal to 5, and this is minus, what was it, minus 1? I don't remember, minus 1, sure. So minus 1 to the 3/2 power minus 30 is equal to 24. Okay, let's simplify what's inside the parentheses. 2 times 5 is 10, minus 1 is 9, so 2 times 9 to the 3/2 power minus 30 is equal to 24. Again, I find it easier to take the square root of 9 first and then cube whatever my answer is than to cube 9 and then take the square root of it, because 9 times 9 is 81, and then cubing it means we have to take 81 and multiply it by 9 again, and I don't want to do that. That sounds ridiculous. So what I want to do is I just want to take the square root of 9 first. So the square root of 9 is going to give us 3. So we just have 3 cubed, right? Because that cubed we haven't done anything with. Okay, minus 30 is equal to 24. Okay, I'm going to just draw a line here because that was part of our original work. Sorry, I'm running out of room here, my mistake. So 3 cubed is 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, and 27 times 2 is 54. So 54 minus 30 is equal to 24, and yeah, 24 is equal to 24. Yay, this works out. So we know then that our final solution of x is equal to 5 works. It is not an extraneous solution. This is a good solution. So we're done. Okay, so that took a little bit to work through, but hopefully it makes sense. I want to give you guys an opportunity now to go ahead and do your second classwork assignment. So the second classwork assignment is as follows. It is 3x minus 1 to the 2/3 power plus 5 is equal to 9. Okay, so go ahead, pause the video, give this a shot, see what you come up with, and hopefully it's not too bad. Okay, let's work through this together. So remember, what we're doing is the same thing that we're doing when our radicals are present, right? We're trying to isolate this garbage looking term. It's, that's this piece here to the 2/3 power. I want to put that all by its lonesome, right? So to do that, I have a plus 5 attached to it. I want to subtract 5 from both sides. So subtracting 5 from both sides, we get 3x minus 1 to the 2/3 power. And then subtracting 5 from 9, we just get 4 here, right? Okay, so once again, you can think about it in one of two ways. I will write out both ways one more time. So both ways means that, we can convert it to the radicals, or we can just do that reciprocal fraction of, raise it to the reciprocal and things will work out nicely, right? So converting this to be in terms of radicals and whatnot, this essentially is saying, okay, well, we have 3x minus 1, and this is going to be which operation makes more sense to do first? And that's kind of what you have to ask yourself when you're converting it to a radical. I think personally it makes more sense to do the cube root on the outside. So we'll have the cube root on the outside, which means that we have 3x minus 1 squared cube root on the outside, right? And where am I getting this from? Well, I'm getting this from the square. This piece is coming from our numerator, right? The numerator of our fraction. So right here. And then the denominator of our fraction in the exponent implies the index of our radical. So in this case, it's going to be a cube root because the denominator was 3. Okay, and now this is equal to 4, right? And now we just have to undo operations, right? So if we have the cube root, we're going to cube both sides. So cubing both sides. Oops, I had a 3 in my head and I wrote a 3 there instead of the parentheses. My mistake. Okay, so cubing both sides, that's going to cancel here, that's going to cancel here. We're left with 3x minus 1 squared is equal to, 4 cubed. Well, 4 cubed is going to give us what? 4 times 4 is 16 times 4 again. Well, 16 times 4 is 64. Okay, so now all we have left to do is we have to undo what we have, right? And this is just considering squares, right? This is going way back to, a couple lectures ago, and you could move that 64 over, you could apply difference of squares, but why do that with such a large number? We're just going to take the square root of both sides, undo, the operations here. So square root of both sides, and of course that means our square is going to cancel, and we're left with 3x minus 1 on the left. But remember, we're solving for a variable here, right? And we just took a square root, so we have to put our plus or minus, right? Don't forget the plus or minus when you're taking an even root. So we took an even root of 64. Square root of 64, I think everybody knows that, right? That's just 8, right? 8 times 8 is 64. Okay, so now we just go ahead and solve. And now 3x, we're going to move that 1 over. So 3x is equal to 1 plus or minus 8. And then divide by 3. X is equal to 1 plus or minus 8 all over 3. Great. And we have our solutions, right? And now this would either be x is equal to 1 plus 8, which is 9 over 3, which would give us 3, or 1 minus 8, which is negative 7 over 3. And you can't simplify that anymore, so negative 7/3. Okay, so that was the first way to think about it. The other way to think about it, which is really what I kind of want to gear you guys to think about, like going this way, this is kind of what I consider your safety net. If you remember that you can just convert it to a radical, then you can just undo your radicals and move on that way. But how I really want you guys to try to think about it is, okay, if I have my 3x minus 1 to the 2/3 power, and this is equal to 4, what I could do is I could just raise the entire thing to the 3/2 power. Why? Remember, I'm raising it to the reciprocal, so that way, when I multiply my exponents together, they will just cross out to be 1, right? And then we'll just be left with 3x minus 1. So and whatever I do to the left, I also do to the right, correct? Okay, so these are going to cross out like we saw before. We're just left with 3x minus 1. And 4 to the 3/2 power Doesn't matter which order you do it in, right? So what I'm going to do is I'm just going to take the square root first, because why not? So the square root of 4 is going to give us plus or minus 2, right? And then this whole thing is cubed, and 3x minus 1. Okay, plus or minus 2 cubed. Well, remember, when you cube a number, it's not going to have that same effect as if you're squaring a number, right? It's not always going to be even. It's going to be whatever your sign is. So we still have to keep that plus or minus 8, right? Because if we had a positive 2 cubed, it would be positive 8. If we had a negative 2 cubed, it would be negative 8. So we still keep that plus or minus 8. And oh, wait, isn't that exactly what we had here? 3x minus 1 is equal to plus or minus 8. Great. So then we know what our solutions are going to be. I don't have to necessarily do the work because we already did the work. And we know that we're going to end up with our negative 7/3 and 3 for our solutions. Right? And now what you have to ask yourself before you move forward is, are we done, right? Could there be extraneous solutions? So we go back up to our original equation, way back up here, right? We look at our variable and we say to ourselves, okay, our variable is to a rational exponent. It's to the 2/3 power, but extraneous solutions can only occur when your variable is under an even root. Is our root even? No, our root is a cube root, right? Our root here is the denominator of our fraction, which is 3. 3 is not even. It implies a cube root. So we actually will not have any possibility of getting extraneous solutions, which means that you do not have to do a check unless you want to check your answers just to make sure that they work out. But I can promise you that if you did, both of these would work out and both solutions will work. Okay, but point is that you should really try to reflect and make sure you understand when and when you won't get extraneous solutions. And in this case, extraneous solutions are not possible. Okay, so this would be our final answer right here. Okay, so we have one last topic to cover today, and then that should be it. And this topic might seem a little bit weird at first, but I think that it'll make a lot of sense once you start diving into it, okay? So what we're going to be talking about today is substituting equations. So when we have, really messy equations, substituting them so that way they can look like a quadratic form. And once again, a quadratic in standard form is ax squared plus bx plus c is equal to 0. Right? So what we're going to do here, our goal is, regardless of what we're given, we're going to be substituting somehow so that way we get something that looks like this in standard form. Okay? So let's look at our first example. Let's say we had x minus 1 squared plus 3 times x minus 1 minus 18 is equal to 0. Now, at first glance, this looks terrible. You have so many terms, you have a lot of things going on, you have an x minus 1 squared, and if you tried to do this by our normal methods, which our normal methods were originally with, pieces like this with polynomials, is you would have to expand that x minus 1 squared, you would have to distribute that 3 to the x and to the negative 1, and then you would have to condense your terms and then try to solve it from there on. And I can tell you, because I have done it, this will work if you do that. So if you do try to do x minus 1 squared, what was that going to, break up into? And when you expand it, you will eventually arrive at the same answer. But there's a much easier way to go about this. So what I want you guys to notice is, first off, what is my hiding power of this term here, x minus 1? Remember, when our power isn't visible, there's technically a hiding power there, and our hiding power is 1, right? And sorry, okay. Our hiding power is 1 there, right? So we have our highest power is 2, followed by the same term, right? X minus 1 here, and then another x minus 1 here, and then this x minus 1 is to the first power, and then we have a constant, right? Minus 18 is just a constant. Well, let's reflect back on our quadratic in standard form. We have some piece here being squared, followed by the same piece, so again, our x, but to the hiding of the first power, right? And then some constant, and now it's in standard form, right? So what I'm going to do is I'm going to assign another variable, and for the sake of argument, I'm going to say u is the variable I'm going to use. You can use any variable, whatever makes sense to you. So I'm going to call it u, and I'm going to assign u to be equal to the entire piece that would make this look like a quadratic. So the entire piece that would make it look like a quadratic is x minus 1. So I'm going to say over here, let u equal x minus 1. And now remember, what does equal mean? Equal means u is x minus 1. So wherever we have an x minus 1, we can plug in a u. So let's do that, and when we do that, we'll see the point of this. So we have an x minus 1 here, right? So wherever we have an x minus 1, we're going to plug in a u. So we have u squared plus 3 times, well, x minus 1, right, to the first power is just u to the first power. And to the first power, I'm not going to write that power, minus 18 is equal to 0. And you say to yourself, oh, wait, this definitely looks like a quadratic, right? We compare this to this piece here. Sure, it's a different variable. It's a u instead of an x, but that doesn't matter, right? It looks like a quadratic now. Our highest power is 2. We have some, some variable to the second power plus a coefficient, 3, times our same variable to the first power, and then a constant. This is a quadratic now in standard form. So we can go ahead and do our normal quadratic things, but we're just considering u. Now, remember what I said at the beginning of this video. We're essentially substituting in so that it's going to look like a quadratic. We can then do all of our normal solving quadratic methods, the completing the square, the difference of squares, factoring, quadratic formula. All of that is going to apply now that we substituted it in to be in standard form. The only difference is that when we're done solving for u, we then have to go back to this piece here and solve for x, right? The original equation is calling for us to solve for our variable x. We substituted it in for u, and so when we solve for u, we then have to just go back and make sure we solve for our original variable, okay? So let's solve for our quadratic equation here. U squared plus 3u minus 18 is equal to 0. Well, I'm going to do this by factoring, right? Our coefficient of u squared is 1, so we don't have to do 8 times c. We just need to look at factors of negative 18. So negative 18, let's see, we want factors of negative 18 so that they will add together to give us a positive 3, right? And that should be pretty easy, 6 and negative 3, right? If I have 6 times negative 3, that's negative 18. 6 plus a negative 3 is positive 3, right? So u plus 6, u minus 3 is equal to 0. Great, we're going to go ahead and solve now. Zero product property, same exact thing. So solving this, we get u is equal to negative 6 and u is equal to 3. I just, I skipped the step of writing down u plus 6 is equal to 0 and u minus 3 is equal to 0, but you guys can do that. I have faith. So u is equal to negative 6 and u is equal to 3. Great. Remember, though, we're not done, right? Our let statement, what was the relationship between u and x? U is going to be whatever x is, but minus 1 from x, right? So we're going to plug in our solutions that we got for u into the relationship that we set up. So we have negative 6 is equal to x minus 1, right? U is equal to x minus 1. And if u is negative 6, we can just plug that in there. And same thing over here, right? 3 is equal to x minus 1. And then doing the same thing, we're just solving now for x. Add 1 to both sides. So adding 1 to both sides, we get x is equal to negative 5. And adding 1 to the right side, we get x is equal to 4. And we end up with our final solutions here of x is equal to negative 5 and 4, right? So does this make sense? Is this what we're trying to do? Well, yeah, it should, right? And again, in theory, this is exactly what we are trying to get, because what we're trying to do is we're just substituting in to make it look like a quadratic. And now that it is a quadratic, we just solved the quadratic. The only difference is we're just plugging in our u back into the original equation that we set up, the relationship with x, so that way we can find our original variable. So you guys would normally be used to, if I gave you just this piece here, you guys could totally do that, right? If I gave you u squared plus 3u minus 18 is equal to 0 on a quiz, you guys could totally factor this, solve for u, and you'd be done, right? The only thing is that u, again, we set up such that it was equal to x minus 1. And we needed to solve for x minus 1, and so we did. And so our final solution set is x is equal to -5, 4. And we're done. Okay? Okay. Let's look at one more example together, and then I'll let you guys go on your last classwork assignment, okay? So let's do another one together. Okay, let's say that we had, sorry, I thought I had one more. Maybe I didn't have one more. Oh, well, cool. You guys we'll just jump right to your classwork assignment then. Okay, perfect. Never mind then. Sorry about that. All right, so classwork assignment. All right, x to the 2/3 minus 7x to the 1/3 plus 6 is equal to 0. Okay, so my mistake. Thought I had one more example, but I didn't. So we'll just jump to this classwork assignment. And yeah, so feel free to give this a shot. Again, as a hint, I know this looks really weird. You have x to the 2/3 power and x to the 1/3 power. It's like, what are you doing? Remember your goal, right? Your goal is you're trying to get it in the form of this here, right? ax squared plus bx plus c is equal to 0. Don't get hung up on the name of the variable because you're going to be naming your own variable here, right? You can f, z, whatever you want to call it, doesn't matter, right? Just it can't be x. So, but your goal is whatever you substitute into, you're going to be trying to make it look like this form here, okay? So give this a shot. See if you can even if you don't solve the whole thing, see if you can just get the substitution right, so that way you can get it looking like a quadratic in standard form. So give it a shot, see what you come up with. All right, so let's go through this together. Probably the worst part of this entire process is trying to figure out how you're going to substitute things so that way you can end up looking like a quadratic, right? Okay, let's do one more quick refresher on exponent rules. And the reason that we should do this is because, well, we have a rational exponent, right? So remember when we had a to the m times n, we can go backwards, right? We can split it up as a to the n, right? Or other way, it doesn't matter how you split it up. You could also do a to the m to the n, right? You can, if you had two numbers being multiplied together for your exponent, then you could split it up into, your base raised to an exponent raised to that other exponent. So that's what I want to do here. So let's consider x to the 2/3 and also x to the 1/3. So considering x to the 2/3, well, what is x to the 2/3? I'm sorry, well, let's just look at the fraction. What is 2/3? 2/3 is really the same thing as 2 times 1/3, right? So we can split this up as x to the 1/3 power squared, right? All we're doing is we're splitting our fraction up because we know that 2 times 1/3 is 2/3. So we know that we have two numbers being multiplied together. And our goal is we want to end up with a square, right? Our goal is to get this looking like a quadratic. So when we substitute in for whatever we're going to substitute in for, we should have our highest power being a square. Again, quadratic equation means, again, our highest power will be a 2. So if our goal is to get a 2 on the outside, then just split up 2/3 so that way you get a 2 on the outside and whatever is left is left. In this case, 1/3 is left. Okay, same thing, right? So x to the 1/3 power. And now this might seem a little counterintuitive, like we're cheating, but 1/3 times 1 is still just 1/3, right? So 1 times 1/3. Again, it doesn't seem like there's a 1 hiding there, but you can take any number and multiply it by 1, and we still get that same number back, right? So what I'm going to do is I'm going to split this up into x to the 1/3 power, and then the first power on the outside. And why can we do that? Well, again, 1 times 1/3 is just 1/3, right? This simplifies back to be that, the same way that this simplifies to be that. All we're doing is we're just splitting things up by our exponent properties. And the reason that we split up x to the 1/3 to the first power is because when we look at our standard equation, what is our middle piece? Well, it's to the first power. So now it becomes really apparent what we're actually substituting in for. We have this piece here to the second power and the same piece to the first power. So what I'm going to do is I'm going to say, let u equal x to the 1/3 power. And we know that if we wanted to convert later, 1/3 power means the cube root of x, right? That might come up later, it might not, but it's good to keep that in the back of your head that essentially this would be the same thing as x, the cube root of x, right? But we don't need that for right now. All we needed to do was just have our substitution ready. So now we know u is equal to x to the 1/3. That's what we're going to substitute in for. So substituting in for what we just have, we now have u squared minus 7u plus 6 is equal to 0, right? Remember, we split up that x to the 1/3, I'm sorry, x to the 2/3 to be x to the 1/3 to the square, right? So that's why we have u squared. And we already just established that this piece, x to the 1/3 power, is u. So u. And now this looks like a super easy quadratic, right? We can totally solve this together. So solving this, again, we just look at powers of our constant, or I'm sorry, factors of our constant, which is 6. So we need two factors such that they're going to multiply to give us a positive 6, add to give us -7. And you say, oh yeah, -6 and -1 multiply to give us a positive 6. -6 plus a -1 gives us -7. So u minus 6, u minus 1 is equal to 0. Fantastic. Let's go ahead and solve this. And we get u is equal to 6. U is equal to 1. Okay, we're almost done, right? We solved for u, which is great. We were able to get it looking like a quadratic. We did our substitutions and we solved. The only thing is now we have to solve for our original variable. Our original variable is x. So because our original variable is x, we have to go back to our relationship that we set up. Our relationship was whatever we solved for u, that's going to be equal to x to the 1/3 power. So we go over here and we say, okay, so 6 is equal to x to the 1/3 power. And also 1 is equal to x to the 1/3 power. Okay, so solving for this, we have x to the 1/3. The way that we get rid of that is we cube both sides. And remember, that should make sense because like we just talked about, this is really the same thing as the cube root of x, right? And how do you get rid of the cube root? You cube both sides. So all I'm doing is I'm going to cube both sides. So I get 6 cubed is equal to x. And 6 cubed, I don't expect you guys to know this off the top of your head. 6 cubed is 216. So 216 is equal to x. And same thing over here, right? 1 cubed is equal to x. And great, 1 cubed, way easier than 6 cubed. 1 cubed is just 1. Okay, and now the only thing is that maybe we should go through and check this. We don't necessarily need to check this because what is our variable under the root? Our variable is under a cube root, right? So that means that we don't expect to get extraneous solutions, but we did end up with a pretty high number here, 216. So it might be worth it to go through and check this. So let's check one at a time. So check x is equal to 1 first. This one will be really simple, right? So wherever there was an x, when we're doing our check, we're plugging in 1. So we have 1 to the 2/3 power minus 7 times 1, once again to the 2/3 power, plus 6 is equal to 0. Okay, 1 to any power is still just 1, minus 7 times 1 to any power, still just 1, so 7 times 1 is just 7, and plus 6 is equal to 0. 1 minus 7 is -6, plus 6 is equal to 0. Hooray! 1 works out. We know that that one's good. Okay, let's go ahead and check 216, which I know seems quite ridiculous, but it should work. So check x is equal to 216. Great. So we get 216 to the 2/3 power minus 7 times 216 to the 2/3 power plus 6 is equal to 0. Okay, so you could do a calculator here, right? You could, just plug this into a calculator and sure, it'll spit you out an answer. But there is a slightly better way, and the slightly better way, sorry, I'm looking for something in particular. The slightly better way here we go, is that we just solved for, 6 cubed is equal to 216, right? We know that 6 cubed is equal to 216, right? So if you take the cube root of both sides, we're just going backwards, right? Because that's what we have to do here. We're going to start by taking the cube root of 216, and then we'll square it afterwards. So if I take the cube root of 216, that's essentially taking the cube root of 6 cubed, right? So cube root 216, it's the cube root of 6 cubed. Great. Well, I don't know what this is going to be, but I know that that's going to cancel and that's going to cancel. So great. The cube root of 216 should just be 6. So cool. And feel free to verify that with a calculator if you didn't see that immediately, but that's all it should give you back. So we get 6, and remember, it's still 6 squared, right? We haven't done anything with that square yet, okay? Minus 7 times 6 squared, right? We still have that 6. Oh, I'm sorry. This is to the first power. My mistake. I'm really glad I caught that now instead of later on. So 6 to the first power plus 6, and I think I made that same mistake here. Yeah, I did. Sorry about that, folks. I was writing too fast. So 1 over 3. And remember, the reason it's 1/3 is because this was our original equation, right? We had the 1/3 here. Sorry about that. My mistake. But again, glad I caught it now instead of after I was done with the video. So we have 7 times 6 to the first power plus 6 is equal to 0. 6 squared is 36 minus 7 times 6 is 42. Again, 7 times 6 to the first power is just 7 times 6 plus 6 is equal to 0. And 36 minus 42 is -6 plus 6 is equal to 0. Hooray! This works out once again. And now we have verified that both solutions are, in fact, good solutions. So our final solution set is x is equal to our solution set of 1 and 216. We are done. Okay, so this is a really useful method to have in your arsenal of tools, because realistically, how else are you going to try to solve x to the 2/3 minus 7x to the 1/3 plus 6 is equal to 0? We don't have another way in our arsenal right now. You could, in theory, if you wanted to, you could cube everything. So the only other way that comes to mind is you would have to move, isolate one of your pieces. So I would isolate the x to the 2/3. I would move everything over to the right hand side. I would try to cube everything because we have the cube root as a piece here. But then what you would end up having is, if we did try to brute force it, we would have x to the 2/3. Sorry, that's a 3. I know it doesn't look like it. Is equal to 7x to the 1/3. And then we would have the -6, right? And then what I was saying is, to brute force this, you would cube both sides. But cubing both sides, yeah, that would help you with the left-hand side, and you would end up with an x squared here. But you would also end up with 7x to the 1/3 minus 6 cubed, and nobody wants to do that. That sounds horrible. I would never make you do this on a quiz. So please remember how to substitute. Remember that you're trying to get it in the form of a quadratic, because that way it'll make your life way easier than trying to do something like this. Okay? But yeah, that's it, guys. Thank you for for trying the classworks, for listening to the lectures. I will see you all in the next class. So have a great one, and I will see you next time.